Great. So let's look at how we would go about solving this continuum approach. So it might be easier if I stand this side as well. Make sure I get my finger where it needs to be. Okay, so what we have here is we essentially have this expression here that's now integrated from 0 to 1.5 of this expression, and we want to say let's minimize this expression. Okay, let's try and find the minimum of this. So first off, what we can do is to say, okay, like we've done before, we took in the discrete approach, we set up a system that was sort of an error, and then we took the derivative with respect to the variables that we were going to try and find sort of a place where we could set the gradient equals to 0, because we knew the shape was nice and convex. And the same here, we know that this is sort of errors. This is a residual squared, so this is also going to be something that has got a nice sort of convex shape. So if I can set the gradient equal to 0 of this expression, okay, if I can do that, then I'm home free. I can say, beautiful. If I can set the gradient equal to 0, then and solve for that gradient equal to 0, then I could solve for this system. So let's go and do that. So this is sort of the final result. So here's the final result that we've sort of obtained. But I just want to make sure that we first just go through this and actually just go and write it out. Okay. So what we have here is that we have the integral from 0 to 1.5 v of x minus ax squared plus bx plus c, yeah, and all of this is now integrated. Just write it like this. Integrated from over dx. Okay, so that's all on the board still. Beautiful. Okay, so that's all good and well. And this is then this whole thing squared. That's what we have. Okay. So what I wanted to do is now say, let's take the derivative of this expression with respect to a. Okay, so that's essentially what we can do. We can say, let's take the derivative of this expression with respect to a. What do we get? So I'm going to just this time do it explicitly. Last time I did this, I had it already nice in the format of z, so I could take the gradient of this. Here I'm just going to say, let's take the derivative with respect to a, and then with respect to b, and then with respect to c. So I'm going to get 3 partial derivatives. So I'm going to say, this is e, okay, which is a function of a, b, and c. You can see there, sort of e, function of a, b, and c. Okay, I could have also called it z if I wanted to, but in this case it's just written like this. So I'm going to say, let's take the partial derivative of e with respect to a. Let's compute that and say, what is that? That is essentially this expression. So it's 2 times. So this you can think of as now as expression as something as a function of that a. That's 2 times 0 to 1.5 v of x minus a x squared plus bx plus c. Okay, so I'm taking the derivative of this, that's 2 times this, and then the derivative of this term here. What's the derivative of this term? It's minus x squared. Okay, that is essentially what I have from that. And then make sure it's still on the board. I can write in the dx. Okay, if I tell you what is the partial derivative of e with respect to b, it's again this expression, this whole thing squared, so it's 2 times 0.15 of v of x minus ax squared plus bx plus c, all of this, and then the derivative of the inside. What is the derivative of b here? It's just minus x dx. Okay, remember the minus there. Okay, and then the derivative of e with respect to c, the partial derivative of that, it's just again, this expression is squared, 2 times 1.5 v of x minus ax squared plus bx plus c, and then the derivative of c with respect the derivative of the inside with respect to c is just minus 1. Okay, dx. That is what I have. Okay, so these are the 3 expressions that I have, and I would like to set this now equals to 0. So I would like to say, see, I don't have space there, but what I would like to say is that this is equal to 0, and that this is equal to 0, and then this equal to 0, because these are the components of the gradient vector with respect to the variables a, b, and c. So what I want to say is this must be equal to 0, this must be equal to 0, this must be equal to 0. That's what I would like to do. Okay, so let's go and see if we can write this maybe in a more convenient form. And for that I'm going to say, for 1, I can divide out by all the 2's. So the 2's can disappear out. I can divide by 2 because it's just equal to 0 that side, equal to 0 this side, equal to 0 on this side. Yeah? I'm just making sure the video is running. I had 1 or 2 mishaps this morning. Okay. And then essentially, so what I can do now is to say, fantastic. let's take all the terms with, let's take this first expression, all the terms with an A, B, and C. We can maybe write it into sort of C and a matrix. So I'm going to write some matrix in here and then say I'm going to multiply with A, B, and C. And then I'm going to have some right-hand side here. And on this right-hand side, I'm going to have essentially, hopefully, some stuff that I can add in there. It'll be a function of the constants like the V of x's and stuff like that. Okay, so let's see what we have. So when I look at this first expression, that's going to be my first row. It's going to be this first equation I'm right here. Second row is going to be this one, and third equation here is going to be this derivative. So let's start with this first one. This expression here, if I multiply this out, this becomes then plus ax to the power 4. Is that correct? So can you see that? So that's essentially, this will become an integral from 0 to 1.5. So what I'm going to do is, please bear in mind, I'm just going to write integral, not the 0 and 1.5. It's going to get too small. So I'm going to write integral. It's implied. So when I write the integral, what I imply here is the integral from 0 to 1.5. Okay, just it's going to be easier. And I might omit the dx at the end, just to save some space. But essentially, this will become then, so this is minus x, x squared times this minus x squared. So this will be then x squared times x squared. Okay? That is essentially what I have. 4, but I want to keep it x squared, x squared. I want to be able to have these terms recognizable at the end. So that's that. I'm going to omit the dx, but it's implied when I write that. Okay. So this implies this some expression dx. Then I've got the b term. The b term is what? It's a negative b of x times a negative x squared. So that will be the integral of a x dot with an x squared. Okay, and that will be sort of what the b multiplies with. And then the c will multiply with, essentially the negative c will multiply with the x squared. So that will be the integral of essentially 1 multiplied with x squared. This is what the c will multiply with. Okay. And then I can go through the next equation. But before I do, what is left? What have I not touched? I haven't touched this one. So all of these terms are now in this matrix. This term I haven't worked with. So this is essentially v of x multiplied by the x squared. Yeah? And I want to take it to the other side. So that is a negative v of x, negative x squared times v of x will become a positive. So that's be v, the integral of, so integral of v of, let's go write it as v x squared. Okay, and again the dx is implied. Okay, this is v of x. Just writing it now as v. Okay, so that's that. And then I can say the second expression, we go through the same story. This will become negative x squared minus, this time it multiplies not with x squared, but with a negative x. This will just become x squared dot x. This will become bx minus bx, so that will become x dot x. This will become essentially 1 multiplied by x, so this will become 1 multiplied by x, and this v of x will multiply with a negative x, take it the other side, becomes a positive, so it will become vx. Okay. And then lastly, the same thing. The last equation is just multiplied by 1 instead of an x, so this will become x squared times a 1, become a x times a 1, and then it will become a 1 times a 1. Okay. So just let's put the dots there just to make sure the multiplication is clear. Okay. This just means 1 times 1, x times 1. That's all that it implies. And here I essentially have v multiplied by 1. Okay. Put the dots here as well just to make sure that this looks, so it's easier to see which terms are where. Okay, so that's essentially what we have. This is the system we have. And if you go and look here, do this expression here, you can see sort of exactly the same terms that I've got there. Okay, so we've got the x squared. I think I've written it, yeah, same way. It looks very, very similar form. But you can now compare what we've got there. And this, what it means is, once I've solved for this a, b's, and c's, this is the a, b's, and c's that minimizes this expression. Yeah, because we've taken the derivative, set it equal to 0, and that's what we've got. Okay, so this now at least we understand where this is also coming from in this continuum approach. But what I want you to pay attention to at this stage already is, look at the number of integrals. It's an integration nightmare, yeah? And this is what a big part of a finite element method is we're going to be computing many, many times integrals. Can you also see, again, just as a reminder, if I ask you for a 9th order polynomial or a 6th order polynomial to fit it through the data, yeah, how big this system would be, how many times you would just do very basic mundane stuff Can you see the benefit of Python? Hopefully you'll make it's clear to you that this is something that can become very tedious. It's really a joke to integrate these things. Nothing difficult about it, yeah? But it becomes tedious if you just do it over and over again. And this is why the finite element method, really, because this is the first step towards the finite element method. It's same type of thing, just in a slightly different way, but it's a function approximation, and function approximation. And the fact of the matter is, it didn't take off until the computer got invented. Okay, finite element method really started taking off in the late 50s, early 60s, and it bloomed in the 70s because the computers started coming out, and these things are fantastic for computers to compute, but it's really, really mundane for humans to be involved with this. Okay, so hopefully, again, I'm going to make it clear in this course. This course is the challenges of this course is not to integrate these things. That's a joke that you could have done in first year already. The challenge of this is to understand various ways we can construct these systems, various ways we can maybe break down this field of x from 0 to 1.5. Maybe we want to chop it into smaller pieces. That's already then getting us our first steps towards the finite element method. Okay, so this is just, I'm going to leave it here, and I'll start the next video where we're going to continue on with this. At least we understand with this slide where things go.